Alright, this shouldn't take too long. This right here is kind of the crux of what we're going to be doing for the rest of the chapter. We're going to be doing a lot of simplifying radicals. We've done a little bit of this. We've seen parts of it. So now we're just going to do a little bit more of a deep dive into the primary process that we use for simplifying radicals. Power, product rule and quotient rule, they go really hand in hand with exponents. But instead of checking for the same base, now we're looking for the same index. As long as we have the same index, we can write radicals in a couple different ways based on whatever is going to be most useful to us at the time. Okay? We can either split it into two separate radicals, or we can write it as one radical. The index stays the same. It's just how we're writing those factors is going to differ. Okay? So to start, what we're going to do is we're going to take two radicals with the same base and combine them into one radical. As long as the indexes match, then I can write them as their factors under one radical. Well, what's 7 times 5? 35. So the square root of 7 times the square root of 5 equals the square root of 35. Okay? So what do we think about for the square root of 31 times the square root of x? 31x. Bring them together under the same radical. Again, checking the index. Third root of 9 times 3. 27. Now this one's a little bit different than the first two because I can take the cube root of that product. It gives me 3. Okay? So sometimes once I multiply them, I might be able to simplify it a step further. So that's something you need to be on the lookout for. Alright? 6th root. So since the indexes match, I'm going to have 6y to the 4th times 3x to the 4th. 18. X to the 4th. And y to the 4th. Okay, so we're just multiplying those radicands together. Simplifying when we can. I can't do the 6th root of 18 or x to the 4th or y to the 4th. So those are as they are. Alright? Quotient rule, same idea, but now we're dealing with division instead of multiplication. We did this a little bit before when we had the square root of a fraction that was a perfect square, such as 1 over 9 or 25 over 36. You guys were pretty good with those in the beginning. This is more useful when we have either a numerator or a denominator that is not a perfect square, which is why it helps to split it apart. So for my quotient rule, I'm going to write this as the square root of 36 over the square root of 49. What's the square root of 36? 6. And then 49? 7. Okay? Easy enough, but those were both perfect squares. When we look at b, x is not a perfect square. I can't square root x, but I can square root the 16. So this is when the split is really important. I have the square root of x over the square root of 16. I can square root the 16 to get 4, but the square root of x will just stay the square root of x. Can't do anything else with it. So I can simplify part of it and leave the other part unchanged. Is 27 a perfect cube? What's the cube root of it? And cube root of 64? 4. Easy enough. Can I 4th root 4? No. So I'm going to go ahead and split this all apart. I've got the 4th root of 4 over the 4th root of 81 and the 4th root of y to the 8th. So this is a combination of product and quotient because my denominator has 2 factors. So I'm going to go ahead and multiply and split those into 2 factors, and then I've got my numerator. We already said we can't 4th root 4, so that just stays. Okay? 4th root of 81, 3, and the 4th root of y to the 8th. y to the second. Okay? Now, can I square root 40? No. Does 40 have a factor that I can square root? What? Not 5. 4. So let's factor 40 into the square root of 4 and 10. 4 is a perfect square factor of 40. So then when I split it, using my product rule, I can take the square root of 4 to get 2. 10 does not have any other perfect square factors, so we leave it as 10 square roots of 2. I'm sorry, 2 square roots of 10. Put the number backwards there.
Does it matter if we write it with the multiplication?
You'll almost never see it though.
You say almost.
Well, he's going to write it, so. Not 915. Because this one I don't want perfect squares, I want perfect cubes.
27 and 5.
27 and 5. Okay, so 27 and 5. This is where it becomes really, really helpful that you are familiar with a lot of the common perfect squares, perfect cubes, even some that are common fourth powers. For your perfect cubes, 8, 27, 125, it helps to know those numbers so that you can recognize when we have those factors. Or at least that you know that those are factors you should be looking for. Okay? Make sure that you're aware of a lot of the common perfect squares so you know to look for those factors. So when I split this, what's the cube root of 27? 3. And then I've got the cube root of 5. Please, 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 for my sake and mostly for your grade, make sure that there is a clear differentiation between the index and the coefficient. Okay? I will say I saw some square roots yesterday that were written like this, but the 3 was the index, so there was a number in front, but it was supposed to be the index, and you wrote it too big. Make sure that your indexes are written smaller than the rest of your numbers inside the crux of that radical symbol, and your coefficients are clearly differentiated from them. All right, because I'm not going to make any assumptions. If that looks like a 33 root 5 to me, it's wrong. Okay, so you need to be aware of that. Now, factors of 15. 3 and 5. Can I square root 3? Can I square root 5?
No.
Then this is already simplified.
That's what we write.
Already simplified. Okay, same idea, but let's toss some variables into the mix. Square root is 36 a perfect square? Cool, so I can leave it with 36. Is x to the 7th a perfect square? No. So now I need the largest exponent, less than 7, that is a perfect square. Bigger, 6. Because I want something divisible by 2, so I just need to go down for 1 on that one. Now, if I factor out an x to the 6th, what do I have left? X to the 1st. Okay? So now that I've split it into my factors, I can go ahead and do each root. Square root of 36. Square root of x to the 6th. Not x to the 2nd. Third. And then the square root of x. Okay? If you want to help differentiate between the coefficients and the radical, you can go ahead and just toss that into parentheses, and that'll help separate that so you don't mix up the exponent with the radicand or the index. So you can do that as just a little extra, differentiation. Is 54 a perfect cube? No, it's not. Neither of those are perfect cubes. Say again. Okay. Is x to the 6th a perfect cube? Is 6 divisible by 3? Yeah. Cube root of x to the 6th. What about y to the 8th? 8 divisible by 3? No. So, biggest number smaller than 8 is divisible by 3. So we'll have the third root of y to the 6th.
Y squared.
And then we'll be left with y squared. Okay? Alright, so let's start with 27. Cube root of 27. 3. I can't cube root 2. Cube root of x to the 6th. X squared. Cube root of y to the 6th. Squared. Okay? And then inside the radical, what am I left with?
2y.
Not y to the 6th. I turned y to the 6th and then y squared. So just the y squared. Both of those go back into the radical. And there's my final answer. I'll put parentheses around that to separate the exponent from the index. Okay. Quotient rule, same thing. We want to split it apart and then simplify. Okay? So there's a couple different ways that we can look at this one. If we use the quotient rule, we're going to put it under one radical. So I have the square root of 72 over 2. Well, what is 72 over 2? 36. So that turns it into the square root of 36, which equals 6. Alternately, what we could have done is we could have split this apart as the square root of 36 and the square root of 2. Now I have common factors in my numerator and in my denominator. I can eliminate those and I still end up along the same root. Either way is fine. Knowing how we can manipulate the equation, often in a couple different ways, in order to get the same end result. Okay? So if we take this big radical and write it under one radicand, I've got 4 and then the cube root, make that bigger, the cube root, 4 cube root of 56x to the 5th y to the 8th over 7y squared. So let's look at what we can simplify. 56 divided by 7 gives me what? Gives me 8. So 4 times the third root of 8. Okay, so I simplified those to give me 8. There's nothing numerator and denominator with x to the 5th, so that stays. And then I've got y to the 8th and y squared. What does that simplify to? Y to the 4th. No, not y to the 4th. Y to the 6th. Thank you. Subtract. Okay? Well, now I don't have a denominator anymore. So that makes it a little bit easier. So then I can look and say, okay, well, let's split this apart now so that we can do all of our perfect cubes. So again, 4 stays the same. Third root of 8, that's fine. No issue there. Can I take the third root of x to the 5th? No. So what's the largest number less than 5 that can be divided by 3? 3. That's a mouthful, right? What am I left with? X to what power? Squared. Okay. Y to the 6th, perfect cube. Good. Okay. So to finish that up, I've got 4 times, what's the cube root of 8? 2. Cube root of x to the 3rd.
So 30.
Just x. 3 divided by 3 is 1. And then cube root of y to the 6th. Y squared. So I've got that one, and that one. Simplified, simplified, simplified. Okay, I brought the 4 down. Still left with the third root of x squared. Brought that down, brought down the 4. Just clean this up. What's 4 times 2? 8xy squared